Hello, everybody. I'd like to thank the organizers for giving me an opportunity to talk with you about some work that my group has been doing in the area of developing fluorescent probes with the eye to use them in biological settings. I'm a biophysical chemist and been using fluorescence for a number of years, so I'm excited to tell you about what we've been doing recently. So why would we use fluorescence as a detection method? So first of all, it's very sensitive, so we can even do single molecule work and subnanomolar work, but also working in weaker, higher concentrations and weaker situations for sure. It's convenient unless you have a specialized setup, you can use a plate reader or a benchtop fluorimeter to make measurements. A couple of my favorite things about it is it's versatile. You can measure a lot of different kinds of things with fluorescence. Not all techniques are like that. We can do sizes and distances, equilibria, kinetics, and that sort of thing. And we also can watch things happen in real time. So when we have a probe that's reporting and observing on what's happening in real time, we can actually detect that. And often, if we make good choices about what the probe is, we can put a label someplace where it doesn't interfere with the process that we're observing. So when one goes about choosing a probe to work with, there's a number of things to think about. One is it soluble, and particularly in biological settings, water soluble? Does it have an appropriate extinction coefficient for the measurement? So we're working at low concentrations. We need high extinction coefficients. Of course, if there are weaker interactions, then a lower extinction coefficient would be more appropriate. And we also want good wavelength or emission behavior. A number of dyes, there's quite a bit of a crowd between about 350 and about 500, 550 nanometers. A lot of commercial dyes emit around there. And there's also autofluorescence in cells, which gives a signal in that range. So we want to be careful about choices that we make there. And for that reason, there's an interest in dyes that emit light at 600 nanometers and above. We also want a photostable probes. In other words, as we do the experiment, we don't want changes in signal to actually be because the dye is decomposed, but because there's been some change in the event in the cell. And then also quantum yield. So given the amount of light we put in, how much do we get back out? In other words, emissive versus non-radiative decay. And sometimes we take advantage of that, but in most cases, we want that to be extremely efficient. So for these reasons, one often is compromising on one element in order to accomplish another, and there's a continuing interest in developing new dyes. So what do these molecules look like? So fluorescein is extremely common here, and there's a number of dyes which are based on this basic type of scaffolding, rhodamine being an example. The cyanine dyes, which I'm showing here in the middle, also in a large family of dyes that have that basic structure. And then I'm showing some older dyes like Nile Red and Prodan. All of them will, as you can see, are extensively conjugated, and they have polar atoms, and we can see an intramolecular charge transfer happening across a lot of these molecules. All right, another scaffolding is the fluorine scaffolding. So a fused three-ring system here, and then one can make substitutions off the ends of it and tune the properties of the dye to something desirable. And there's a smaller literature devoted to fluorine-centered dyes. So the compounds that I'm going to be talking with you about are actually fluorine-based. In this case, we're removing the central atom, or replacing a central atom with a heavier main group atom like silicon or germanium, which are right below carbon on the periodic table. And then we can make substitutions at the central atom or around the rings here. When we're focusing on substitutions at the 2,7 position through an alkynyl bridge, this is accomplished via Sagana-Sherritt coupling. It's pretty easy reaction, actually. All right, so what are our goals here? We're interested in testing these compounds for potential use in biological settings, so looking at molecular interactions, but also cellular environments. And we're also using density functional theory, or DFT, to help us guide the design of new probes, and I'll show you a little bit about the power of that as well. All right, so the first series of compounds that I received from my colleague Janet Wilking, who specializes in making these kinds of compounds, are shown here. And the first two questions I had, if we were going to have a project at all, is are they soluble enough in water? For that, we need about micromolar concentrations at least. And the other is, do they emit in water? Because some dyes are actually quenched in highly polar solvents. So the answer to both those questions, gratefully, is yes, or I wouldn't be here talking to you. And you'll notice there's, for these four compounds, the emission peak is shifted a little bit depending on what the R group is. And that means we can tune the behavior of these compounds by changing the R group. So that shows lots of promise. So our first foray into this was one of convenience, really. Because these are so greasy, we thought they would make good probes of lipids or membranes and cells. And a good place to start here is with detergents or surfactants, which mimic lipids. And we did a study of emission enhancements in the presence of different types of lipids, whether they're charged, neutral, or sphetter ionic, usually using the small library 4. And we find actually for Triton X100, which is a neutral detergent, pretty high emission enhancements, around 20-fold. CTAB also quite respectable. The anion detergents, we don't get as much of that, and that's why that is kind of a different conversation. But we see lots of sensitivity here to some surfactants. And then over here, this is just a cuvette image showing just this tris shining a 395 excitation light on it. When we add the Triton, we get a much greater emission as a result. So to take it one step further, we actually made SUVs, small unilamellar vesicles. And the reason these are handy is that we can make measurements in the conventional fluorimeter because they're small enough to not generate scatter in solution. And in all 4 cases, we see an emission enhancement as a result of adding the SUV. So, and some of them, some are higher than others, of course. So the biphenyl here has a much higher enhancement than some of the others, but definitely an interaction with membrane. So that's a good sign. So why is it that we're talking about membranes, and why might that be interesting? So, as many of you know, cellular membranes are made of phospholipids. They have a polar head group, which faces out and in, and the internal outside the cell and inside the cell. Internal to that are hydrophobic chains, hydrocarbon chains. And so it turns out in a membrane, there can be regions that are more rigid or less rigid, and that's indicated by more rigid LO ordered, LD being disordered. And we can change that rigidity by adding or removing cholesterol, or changing whether or not we have double bonds. That tends to result in a little more disorder. So those phospholipid regions which have more disorder have higher polarity and higher viscosity as a result. So changes in polarity and viscosity in a membrane are actually indicative of some lipid heterogeneity. And that is actually linked to a number of cellular processes, and this can include things like stress from exposure to oxidative agents, dehydration, metabolic stress, viral entry, even programmed cell death actually show changes in the lipid heterogeneity. So there's a motivation to understand and develop probes of lipid polarity and viscosity. So how do we measure sensitivity to polarity? And that's something called solvatochromism. So what happens is that the dyes have their own dipole moment. And when we put them in a solvent, that dipole moment interacts. And of course, you excite the molecule as well with light. And that can cause interactions between the dipoles of the solvent and the molecular dipole moment. And in polar solvents, that results in a shift to the red, so a shift to the right. This is some literature data here showing the shift. And then we can compute something called the Stokes shift. Some of you are familiar with this, where it's the wavelength difference in per centimeter between excitation or absorption and the emission. So as we change a solvent, the Stokes shift changes. One can plot that, actually, versus a property of solvents or solvent polarity. And there's lots of different scales, but for this one, this is solvent polarizability. And you get a linear relationship. This is called a Lippert-Mataga plot. And the slope gives you an indication of the sensitivity to solvent polarity. So for this dye, FR0, very good, has a very high Lippert-Mataga slope. And so remember that. We're going to come back to that a little bit later. It also gets some nice color changes as well. So at this point, we had looked at literature data for a number of systems, but often the Lippert-Mataga plot isn't plotted, but a lot of solvent data is out there. And so we were wondering, can we use the ground state dipole moment as an indicator of the potential for solvatochromic behavior in a dye we haven't made yet? So it would be a good design tool. And to that end, I went out to the literature and computed Lippert-Mataga slopes for a lot of systems and plotted that versus computed ground state dipole moment, which we can just calculate those. And you can see there's a nice correlation there. So we think that ground state dipole moments make a good indicator of solvatochromic behavior as well. So based on that, the earlier metallafluorenes that I showed you have low dipole moments, 2 to 3 dBi. The benzaldehyde substituted metallafluorene has a much higher dipole moment, about 9 dBi. So that should be solvatochromic. And then the compound with the melanonitrile substitution on it has a much even higher dipole moment of about almost 15 dBi. All right, so it turns out the benzaldehyde substituted metallafluorine actually is cell chromic. You can see some shifts in the emission wavelength. This is as a function of different solvents of different polarities. We can generate a Lippert Mataga plot, and we get a slope of about 6,500, so quite respectable. And you can see here, these are cuvette images. As we move to the right, we're increasing the polarity and solvent. You can see a color changes as a result. What about the melanonitrile? Here we see it's even more dramatic. So we actually have in water and methanol and the most polar solvents a peak about 600 nanometers. So this is a red shifted dye. And you can see that down here colorimetrically. These are organized by solvent polarizability as we move to the right. You can see that red dye. The Lippert Mataga plot has a very high slope, 17,000, which is quite competitive. Some of the highest that I've actually seen in literature, so that's quite respectable. And then the Nile Red, compared to Nile Red, which is a commercial dye with a solvatochromic dye with a Lippert Mataga slope of about 4,000. So it's quite competitive. Okay, so that takes care of the polarity or solvatochromic aspects of being a lipid probe. But what about viscosity? So this is a sample from the literature. This is DCVJ, and a molecular viscometer will have a rotating bond of polar groups, which will sweep through a solvent solution. And of course, if there's a bit of drag with that, we'll see a change in the fluorescence intensity. And so the way that's done is one makes a series of solutions of differing viscosity, usually involving glycerol and something else like methanol, water, and then measuring the fluorescence intensity. So this is the sample data for a DCVJ. So what about the melanonitrile? So in this case, we actually did some calculations first. And if you'll notice, there's some places in the molecule where we can have rotation. So the oval here is meant to indicate the core of the metallafluorine. And when both the melanonitrile groups are pointing up, we have a dipole moment of about 5 dpi. If they point down, which is away from the methoxy group, that number shoots way up. And of course, which way the methoxys point actually matters as well. So these are very high dipole moments. So it should be, because there's this correlation between dipole moment and rotation, it should be sensitive to viscosity. So here's some preliminary data where we actually show that. This is with a water methanol system, and you can see that the viscosity, which is tracked in blue, correlates nicely with the actual emission intensity as well. So we're going to follow that up with some more detailed studies. All right, what about imaging? So if we go to giant unilamellar vesicles, we can detect those on a confocal microscope, and we can tune whether it's highly rigid or highly mobile, disordered, ordered, by changing the lipid composition and even adding cholesterol. So this is a sample from the literature here. So in this case, in this far panel here, we have a mix of ordered and disordered regions, and that's indicated by differences by green versus blue. So the first step, though, of course, is to make GUVs, and secondly, to detect them. So last summer, I spent some time on that. This is my GUV little bundle of them there. These are much larger, of course, by design. And here, this is confocal image showing that we have stained our GUVs with Nile Red. And then this is, of course, a sample with a metallafluorine with the methoxy naphtha group. And you can see the green here. We were able to incorporate the metallafluorine into GUVs. So got to get better at that, but looking promising. What about cells themselves? We started with yeast. Using Nile Red, which is a lipid droplet probe, we get staining of the yeast cells. And interestingly, when we add a metallafluorine here, this is biphenyl, the biphenyl substituted, it actually co-localizes with Nile Red. So that indicates that these compounds are also lipid droplet probes. All right, so where are we going from here? We'd like to map lipid domains and lipid structures in cells and follow cellular events. And then we're also interested in designing new probes and using DFT as a guide to that design process of those probes. So in the interest of time, I won't shout out all of my group individually, but there's a number of folks who have been working on it. You can see them on the left. And then I have a number of colleagues on our campus who have helped us with various aspects, and I wish to thank them. And I thank you for your attention.